Hello YouTube viewers, welcome to my show Science Thursday. In today's episode, we're gonna continue our topic of robotics, and today we're gonna look into encoders. So you have to understand that we have already discussed about motors, we have already discussed about pneumatics, we have discussed about hydraulics. But what binds them all? Basically, if you are building a robot, you can use almost all three of them. But one thing that you must have, no matter what you do, if you want to build something reliable, precise, and repeatable, you have to use a sense. Basically, it must know what it is doing. Basically, if I say raise your arm like this, now how do you know that you have raised your arm? Because you have your eye giving you feedback, you have muscle that is giving you feedback, you have nerves that is giving you feedback. So we have feedback. That's why we can do whatever you want to do. Now robots do not know that. Like you can simply send it command, hey, spin this motor. It does not know what's happening. It's just like, okay, I got a command, I'm gonna spin the motor. It has no feedback. To have that, you must have encoders, different types, different variety, but you must have it. Now this allows accurate control and use. Can you make a crude robotic system with like let's say pneumatic system? Yes, absolutely. And I already in my pneumatics video I have provided example of doors from bus, like where you have simply the valves only work in like absolute scenarios, like open, keep opening it up like until it's a completely, it reaches a limit switch when the valve is closed, and doing opposite when you want to close it. There is no feedback, there is no precise control rate. Now again, if that's your use case, awesome. But if you want to do something like a welding robot or a medical robot, you have to have encoders. Now encoders are input device. They do not do anything. Basically they are not there as like, okay, hey, stop, or I'll apply brakes or anything like that. They are not there for that. They are only there as a input. They are basically like your eyes. Now all they do is basically, depending on your design, they will read one data, and the data is generally fed back to the main control. Now this is very critical. Computers do not have like same efficiency as human brain, because like the human brain, like you may not even be looking at something and you touch something hot, your hand will respond, because like the feedback system is here only, like before it even gets to your frontal cortex. So in computers we try to emulate something similar. Basically, let's say computer says, hey, cut a square. Okay, then the command will be split into multiple. Okay, cut square means start here, move 10 units ahead, then move 90-degree right, then go 10 ahead, whatever have you. And during this time, the control robotics that is inside the robot, like the motors, encoders and all that, they will be talking back and forth to the control system. Now control system always takes priority when it receives signal from the encoder. So encoder data is very absolute priority. If you have let's say any quality robot that is used for industrial use, if encoder fails, the whole robot will be shut down. They will never risk it. It's like, hey, can I run it without encoders? In principle, should you do that? Hell no. And all your insurance will be destroyed if they ever find out that you have a faulty encoder running your robots. First of all, you may not be ever able to run it. So for this reason, it is quite important, and it gets absolute priority. Like encoder data must get absolute priority. And if you have for some reason bad block diagram, basically your encoder data goes to the operating system, then operating system interprets it, then it talks to the controller, then it interprets what it's supposed to do. Yeah, you're gonna have a bad day. So you have to know, this is the sense of a robot. So how does this work? Like at first I was like, we're gonna talk about this or that, and then I realized very early on, it's like after more research, is that everything that can be used is used anyway. So just a small list, I'm specifying this is a very small list. There are optical encoders, there are magnetic encoders, there are capacitive basically encoders, and inductive encoders, and eddy current encoders. There are even more than this. So you have to understand, if there is a way to make an encoder, somebody have already done it. So everything is used, and each have their own reason. Let's say for some reason you are building an encoder in a MRI machine. Using magnetic system would be unwise, so you will use optical system. But again, let's say you are building a scenario where you have basically X-ray machines. X-ray machines generally have a bad tendency of overloading optical sensors. Again, not everyone, but you do not want to take the risk, so you may use, hey, let's use magnetic system. It's immune to basically X-ray. Or sometimes you want to make your circuit very cheap, you will use capacitive. You have basically calipers like this, they are generally capacitive. And sometimes you are like, hey, I want something precise, robotic and all that, you're going to use inductive. Sometimes let's say you want to measure engine RPM, you will use eddy current system. So you can get, like, there is endless options out there. like. And you can find, like, you may say like, okay, shouldn't there be like only one or two? Like, again, we build this many and there should be only one or two that are, like, very effective and useful. That's not the case, because, like, let's say you are taking a CNC machine. CNC machines cost is not only limited to the build area or the build quality, it's also limited to precision. Basically, the higher the precision, the more expensive your basically CNC will become. Now, if you have a basic CNC, it's like, okay, it's good and all that, it has encoders in the motor, so it has a feedback to check that. However, if you go to very high end one, they will have encoders in the linear rail itself. So if it receives a command, because there is always a bit of lag between your nut bolt and the carriages, they always have a bit of flex, so to say. So encoders in linear rail itself, again, it adds to your cost and software complexity, but it does give you absolute feedback, hey, you have drifted. So you can understand there is always a need for that. And let's say this is a printer encoder. Your printer has a main drum that rotates and takes care of the paper. This has a feedback, so it can literally know A4 paper, it detects and it's like, okay, I'm supposed to keep spinning at, like, say, to 6 rotation or 7, or there is an internal library in the basically the drivers for the printer. So there is a back and forth and happening. All that back and forth is possible because there is an encoder will say, hey, you have spinned 3 times 3 complete RPM, please stop, or things of that nature. So you have to understand it is a very important part. And there is like optical, magnetic, capacitive. Like, I would say just buy this from Amazon, it's quite cheap. So there are two main uses of this. Basically, if you want to use an encoder, depending on what you are actually intend to do at the end result, you will use either, let's say, linear encoders. Let's say for your lathe machine, if you have seen lathe machine, old lathe machine used to rely on the knobs. Basically, we used to count how many rotations of the knob we have done. Now we utilize on something like this, which we call DRO, digital readout, basically. And they have linear encoders. All the carriages that you have, that you move back and forth, they generally provide a feedback to the central computer, and computer is like, okay, you have moved 2 millimeter, you have moved 5 millimeter, you can zero it out and it can still keep counting in the reverse direction. So it's like, okay, 2 centimeters, stop, make a cut, and then you're like, move 2 centimeters more, stop, make a cut. It will keep zeroing it depending on how you want your things to be done. So it's quite important. Like, at this point in time, almost any self-respecting basically high-end machine shop generally have a DRO. And there is rotation, basically rotary encoder, and you are surrounded by it. If you have a printer nearby, it has an encoder. If you have any music system or any TV and all that which has a knob that you can keep spinning continuously, it is an encoder. You have a mouse which has a scroll wheel, it is an encoder. So you have to understand that, like, they are everywhere. They're not just like, okay, very high end and all that. Of course, they are relying on it, but here also, even in your day-to-day life, you will have a smaller version of this. Basically, this is a fancy encoder used for servo motors, but you will have a small version of that in your mouse scroll wheel. So get that there are two main types: rotational and linear. Basically, how many, like 5 centimeters, 10 centimeters, and all that. So they are the two main uses of it. You want to measure something linearly. Let's say you have a hydraulic cylinder, how much it has extended. So in those sort of scenario, you will use this. Now let's say, okay, you have chosen for your robotics, like, I only need rotational. You're like, okay, I have the rotational system. Now what? Now you have two types of it. One type is absolute. Basically, it will tell you where, like, let's say this is my rotational axis, this is how I'm gonna spin, and there is an arm to it. Now this arm is 90 degree and this is 0 degree. Let's just go with it. And you're like, okay, this happened. Like, you send a command. Now incremental system will, all it will do is keep counting 1 2 3 4 5 6 7 8 9 10 degrees. Now when you have incremental, the problem with that is, like, let's say power went out, it does not know where you are. So what they will do, if you are using an incremental system, it will like zero itself back, and you can easily sense this in your printer. Whenever it, like, you start the printer, wherever the print head is, like, it will go ting ting at the other end. It's zeroing itself out because it's running on incremental system. You have to count it. Basically, once you hit the limit switch, it's like, okay, zero everything out, now add, like, 5 steps forward, 6 steps forward. So it's counting every time. Now when you're talking about absolute, it does not have to do that. It's like, I know where I am. Basically, wherever the range is, it knows where it is in reliably. It does not matter whether it's power or not, because as you can see, these are a small pattern that is read by the sensor. Now sensor can read any pattern here, but none of the pattern will repeat. So this pattern is only here, this pattern is only here, this pattern is rotating here. Using the library, it can be like, okay, you are at 90 degree, you are at 88 degree, you are 70 degree, you are 45 degree, whatever happens. Like, it can be like very precise, and it does not have to rely on basically software to keep counting it. Now, increment are generally cheaper. That's why they are used almost everywhere for your volume knobs and all that. And it's also used in your engine RPM gauge. Basically, you have a there they utilize a magnetic system, sometimes Hall effect sensors, sometimes eddy effect sensors, and they will only tell you the RPM. It's like, is it spinning? Yes or no? Is it spinning clockwise or is it spinning counterclockwise? Those are the function of incremental system. Now, if you want to build a robot and it has to be very precise, it has to rely on absolute, where it's like I send the command move 30 degrees and your angle now should be like 75 degree. Like, again, you send the command is like additive command, move 10, move 20, move 15, but something has to keep all is right. Now, generally you can do this in software, which is a bad idea, because again, you can drift, software can miss cycle and software can crash. So in absolute scenario, computer can like absolutely sure, hey, I sent the command to be like, in your relative term you should be at like 12 degree, you are at 12 degree. So these are the two main types. Now, the primary reason we utilize so much encoders in everything, our day-to-day life, is basically this is what we classify as accuracy defining. Basically, how accurate your system is directly proportional to how good your motor and encoder systems are. Generally, if you have a, let's say, good motor, let's say you're like, hey, I want this robot to keep working for years to come, and you're like, hey, I'm going to invest in a lot of good motor. Now, again, motors and encoders sometimes can be sold and purchased separately. So you can be like, okay, I just bought the best of the best motor, and you put some very cheap, like the cheapest thing you can find out from alibaba.com, and you're like, plonk down there. Will it work? Absolutely. Will it work reliably, precisely? No. And if you're like, hey, I want this robot to work for, let's say, 50-60 years, you're gonna be like, hey, I'm gonna buy the best Nikon optical encoders out there. You bought that and then you put that. Again, your accuracy is directly proportional to your encoder. If your encoder is awesome, your accuracy would be awesome. So you have to understand, like, if you want better result, you have to use better encoders. Do not cheap out on it. Even like people who do machine shops, they can tell you, like, if you have a cheap DRO, they are generally capacitive. So side effect of that, it's like if dirt and grime goes directly into between the rail, it will mess up the rating. Not too much, but it will mess it up. But sometimes, let's say you are working in NASA and like precision is like absolute, then you might use inductor calipers. Those do not care, like and there are some systems where you simply cannot mess it up. Basically, you can heat it up, it will still count exactly. You can like put oil in there, it will still count accurately. So depending on your scenario and your requirements, people use different encoders. So better is better result. Now nowadays encoders is also acting as a recording system. Again, encoder itself is not doing anything, it's feeding data to the control system. But nowadays we are moving towards basically where we'll have robots and humans working together. So we'll what we classify as human compliant robotics. Now, in this robotics, you have to quote unquote teach the robot what to do. Basically, you take its grapper or something, whatever have you, like take this and take that. Now, your computer is recording that. How the heck computer is recording that? It's recording the rotation on every joint. How the heck it's doing that? Relying on encoders. So encoders is acting as again an input device, and it allows you to do like take the whatever end you have, and you can program it to do whatever you want depending on the encoder resolution. So it is very necessary, very important. Now, this whole video was a rough idea how big the role of encoders play in our day-to-day life. So you have to understand this. If you want to do any robotics, you want to do any 3D printer, or you want to do any high precision CNC machine and all that, can you do those without encoders? Maybe. Should you do that? Again, up to you. If you're making a school project, it does not matter. You want to make something like something metal, something concrete, something that lasts. Again, you have to invest in encoders. And should you want do you want to cheap out? That's up to you. It will not give you very precision control. So that's up to you. So encoders are a defining factor in our robotics, modern robotics. So this was my presentation about encoders. I hope you got some ideas, some understanding about this. I hope you liked it. In that scenario, please click the like button. If you didn't like it, didn't enjoy it, I would urge you to press dislike, press it twice to show me your extra disappointment, and please leave a comment because I reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.